Section: Introduction. In this section, we explore the impact of synthetic data on enhancing the math reasoning abilities of large language models, LLMs. We investigate how training on synthetic data influences the performance of LLMs, particularly in the context of math reasoning tasks where synthetic data is commonly used. When we train LLMs on positive synthetic responses, we notice an improvement in performance, although the rate of improvement is slower compared to the initial training phase. Specifically, we find that the error rate decreases as the size of the synthetic dataset increases, following a scaling law. Moreover, not all types of positive synthetic data are equally effective. Responses generated by the model itself can be as beneficial as using synthetic data from larger models. This is because responses from similar models are easier for the model to learn from, reducing the risk of memorization during fine-tuning. However, training solely on positive synthetic data can lead to overfitting on irrelevant patterns. To address this issue, we introduce synthetic negative responses, which are responses that do not lead to the correct final answer. By incorporating negative data, we can avoid overfitting and improve the model's performance. We propose a method called direct preference optimization, DPO, to utilize negative responses effectively. To enhance the model's performance further, we focus on critical intermediate steps in the reasoning process. By contrasting positive and negative responses that highlight good and bad choices for these critical steps, we can achieve consistent improvements over using only positive data. This approach helps the model avoid learning from spurious correlations. We develop a conceptual model based on reinforcement learning principles to explain how training on negative data benefits performance. By emphasizing critical tokens in the negative data, we can effectively assign credit to the model's decisions. This approach, known as advantage-weighted reinforcement learning, proves to be more sample efficient than traditional imitation learning when advantages can be reliably estimated. In summary, our study demonstrates the importance of synthetic data in enhancing the math reasoning capabilities of LLMs. We establish scaling laws for both positive and negative data on common reasoning benchmarks and highlight the benefits of incorporating negative data to improve model performance and avoid overfitting. Section Summary. In this section, we explore the impact of synthetic data on improving the math reasoning capabilities of large language models, LLMs. We find that training on positive synthetic responses enhances performance, but the rate of improvement slows down as the dataset size increases. Additionally, incorporating carefully constructed negative responses, emphasizing critical steps, can lead to performance gains equivalent to scaling up positive data by 8 times, helping to avoid overfitting and spurious correlations. Section: Related work. In this section, we explore the use of synthetic data to enhance the performance of language models in mathematical reasoning tasks. We follow a standard approach of fine-tuning a pre-trained language model by providing expert data using teacher forcing, where the model learns to predict the next token based on the sequence of previous tokens. One challenge we discuss is the limitations of this approach for math reasoning tasks and how synthetic data, both positive and negative, can help address these limitations. Positive synthetic data involves generating additional data similar to the expert data to improve the model's math reasoning abilities. However, creating high-quality synthetic math data can be difficult due to the complexity of verifying its correctness. To overcome this challenge, researchers have explored different sources of synthetic data, such as responses from stronger teachers or data generated by the model itself using techniques like reinforced self-training. In our study, we compare the performance of using positive synthetic data from larger models like GPT-4 and Gemini 1.5 Pro with self-generated positive data. We aim to show that learning from self-generated completions can lead to better generalization and prevent the model from memorizing specific patterns. Additionally, we investigate the benefits and challenges of using negative synthetic data, which involves training the model on incorrect completions as well. By pairing correct and incorrect responses for the same problem, we aim to leverage the insights gained from both types of data to improve the model's reasoning abilities. Our goal in this paper is to understand how synthetic data can help in training strong language model reasoners for mathematical reasoning tasks. We collect synthetic data by generating new math problems and their corresponding solutions using highly capable models like GPT-4 and Gemini 1.5 Pro. We ensure the accuracy of the generated answers through a filtering process and define a reward function to verify the correctness of the solution traces. By using both positive and negative synthetic data, we aim to improve the model's ability to reason step by step through mathematical problems. We acknowledge that even the original answers from capable models may contain incorrect reasoning steps, and our approach aims to address these challenges to enhance the model's performance in math reasoning tasks. Section Summary. Related work. In this section, we explore the use of synthetic data to enhance the performance of language models in mathematical reasoning tasks. We investigate the benefits of both positive synthetic data generated by models like GPT-4 and Gemini 1.5 Pro, as well as the importance of negative synthetic data in identifying and unlearning incorrect reasoning steps. By leveraging a combination of positive and negative synthetic data, we aim to improve the reasoning capabilities of language models in math problem solving. Section: Learning from synthetic data. In this section, we explore different methods for learning from synthetic data, (SYN), discussed earlier. We look at algorithms like supervised and rejection fine-tuning, SFT and RFT, using positive and negative solution traces. For SFT, we train a model on positive synthetic data by predicting the next token in a supervised way. We can also use positive solution traces sampled from the model instead of synthetic responses. RFT involves sampling multiple times to create a dataset of positive responses and then applying the next token prediction loss on this dataset. We can also learn from negative synthetic data generated by the SFT policy using a contrastive training approach called direct preference optimization, DPO. DPO trains a policy by optimizing preferences between positive and negative data. Scaling up positive synthetic data can improve test error rates on tasks like GSM 8K and math. By training models on larger synthetic datasets, we can increase coverage under the real distribution. However, scaling the data may not always lead to better performance, as the improvement trends decay with increasing dataset size. Training on multiple positive answer traces from the SFT policy can result in better models compared to training on a single trace from highly capable models. Self-generated positive data from the SFT policy proves to be more sample efficient and can lead to improved model performance. While RFT data may be easier to fit, scaling it too much can lead to test error saturation or worsening performance due to the presence of incorrect or irrelevant steps. This can cause causal confusion in the model, impacting its ability to generalize correctly. In summary, scaling synthetic data can improve model performance, but it's essential to balance the positive and negative data used for training to avoid amplifying spurious correlations that can lead to performance degradation. Section Summary. In this section, we explore algorithms for learning from synthetic data, focusing on supervised and rejection fine-tuning, SFT and RFT. SFT involves training on positive synthetic data directly, while RFT samples multiple times to construct a dataset of positive responses. Additionally, we discuss the importance of positive data from SFT policies compared to highly capable models, highlighting the efficiency of self-generated positive data in training better models. Section: Negative synthetic data enables per-step credit assignment. In this section, we learned that fine-tuning a model on data it generated itself can lead to the model making mistakes that still guide it to the correct answer in some cases during training but may cause problems in other situations. Even if we train the model on positive data with a low-cost verifier, it may not be able to recognize and fix these issues. Simply increasing the amount of synthetic positive data may not solve this problem. Surprisingly, we discovered that training the model on carefully crafted negative data for the same set of synthetic problems can help address the issues seen with positive data. The key is to construct the negative data in a way that allows us to assign credit to each step of the model's decision-making process. We will introduce a conceptual model in this section to explain how to assign credit to each step accurately. By training the model using this approach, we can show that it aligns with the idea of assigning credit to each step. We will also demonstrate that the method we introduced earlier is a simplified version of this broader concept. Through experiments, we will confirm that using negative data improves the model's ability to assign credit to each step and impacts how the model scales. Furthermore, we will discuss how our conceptual model of using negative data is similar to advantage-weighted reinforcement learning. By exploring this connection, we can understand the benefits of using negative data for generalization purposes. We will illustrate this through a study on a simple problem to provide both theoretical and intuitive insights. Section Summary. In this section, we explore how training on negative synthetic data can address the failure modes of positive data by enabling per-step credit assignment. By carefully constructing negative data, we can identify critical steps in a response and emphasize correct completions, leading to more precise problem solving. This approach, utilizing advantage-weighted reinforcement learning, helps improve generalization and suppress irrelevant or incorrect steps in a model's response, ultimately enhancing the utilization of synthetic data. Section: Scaling results for negative data. In this section, we present the results of scaling up negative data for training the DeepSeek Math 7b and Llama 2 to 7b models on GSM 8K and Math. When we look at the figures, we notice that using per-step DPO improves the performance of both models compared to the SFT policy. This improvement continues as the amount of data increases. Moreover, when we consider a specific size of synthetic data, per-step DPO shows significant improvement over RFT on both datasets. Overall, training on negative data enhances the performance by 8 times the size of the synthetic data. We also find that the choice of negative data has a notable impact. By examining the negative data scaling laws, we observe that standard pairing of positive and negative responses does not outperform the SFT policy. This led us to adjust a parameter in the equation for DPO, but we could not completely prevent performance decline. Our analysis suggests that training with DPO using arbitrary positive and negative pairs can introduce misleading correlations that boost the induced advantage function. Furthermore, we explore the concept of credit assignment from negative data and its role in improving model generalization. When we sample preference pairs according to a specific distribution, per-step DPO acts like advantage-weighted RL. This means that per-step DPO can effectively assign credit by distinguishing crucial steps from irrelevant ones through advantage estimates. This approach enhances test performance and scaling trends compared to SFT and standard DPO using the same data. The advantage-weighted RL objective provides gains in generalization, leading to improved model performance.